Welcome to this lecture on human physiology. Today, we are going to explore a fascinating and absolutely vital topic, action potential conduction. If you have ever wondered how your brain communicates with your toes in a fraction of a second, or how a thought turns into a physical movement so seamlessly, you are in the right place. We will build your understanding from the ground up, starting with simple analogies and moving all the way to the underlying physics and mathematics. Let us dive in and uncover the incredible electrical highway inside your body. To begin our journey, let us imagine you are sitting in a massive sports stadium. Suddenly, a group of fans stands up to start a stadium wave. As they sit down, the people immediately next to them stand up, and this ripple effect continues all the way around the arena. Notice that the people themselves do not run around the stadium. They just stand up and sit down in their specific spots. Yet a visible wave travels a great distance. In our bodies, action potential conduction works exactly like this stadium wave. Instead of fans standing up, we have tiny electrical gates opening and closing along a nerve fiber. They pass the electrical signal down the line without any single molecule having to travel the entire distance. Now that we understand the basic idea through our stadium analogy, let us look at the formal biological definition. Action potential conduction, also known as propagation, is the physiological process by which an electrical signal travels along the axon of a neuron to its terminal. When one segment of the axon membrane depolarizes, it creates a local electrical current. This current spreads to the adjacent resting segment, changing its voltage and causing voltage-gated sodium channels to open. This generates a brand new action potential right next door. Crucially, the previous segment enters a brief resting phase called the refractory period. This ensures the signal can only travel forward in one direction, maintaining clear and organized communication. Understanding how this signal travels naturally leads us to ask why this specific mechanism is so crucial for human survival. Without action potential conduction, your brain would be completely isolated from the rest of your body. You would be unable to send commands or receive sensory information. For example, if you accidentally touch a burning hot stove, this conduction is what allows the pain signal to reach your brain and the movement signal to reach your arm muscles in a fraction of a second. In debilitating diseases like multiple sclerosis, the protective myelin sheath around nerves is destroyed. This severely slows down or completely stops the conduction process, proving that the precise speed of these signals is absolutely vital for movement, sensation, and life itself. Knowing how vital this speed is, we must establish a way to measure it, which brings us to our first mathematical representation. The most fundamental way to measure how well a nerve is functioning is by calculating its conduction velocity. Conceptually, this comes from basic physics, relating the distance traveled to the time it takes. In this formula, v represents the conduction velocity, measured in meters per second. The variable d stands for the distance the action potential travels along the nerve fiber, measured in meters. Finally, t represents the time it takes to cover that distance, measured in seconds. If the distance increases while the time remains constant, the velocity must be higher. Conversely, if it takes more time to cover the same distance, the velocity decreases, which often indicates nerve pathology or damage. Before we move on to more complex properties, let us see this velocity formula in action with a concrete example. Suppose an electrical signal needs to travel from your lower spinal cord all the way down to a muscle in your big toe. We are given that the total distance is 1.2 meters, and clinical sensors show it takes exactly 0.01 seconds to arrive. We need to find the conduction velocity to determine if the nerve is healthy. We choose our basic velocity formula because we have distance and time. We substitute 1.2 for distance and 0.01 for time. Dividing these gives us 120. This final answer means the nerve impulse is racing down your leg at 120 meters per second, which is roughly 268 miles per hour. Now that we have calculated basic velocity, we must ask why some nerves conduct signals so much faster than others. To truly understand this, we must look at the physical properties of the axon using a concept from cable theory called the length constant. The length constant determines how far an electrical current can passively spread down the axon before it decays and loses its strength. A larger length constant means the signal travels further before needing to be regenerated. This results in a much faster overall conduction velocity. This physical principle explains exactly why our bodies use myelin insulation and wider axons to speed up important reflexes. This concept of passive spread leads us directly to the mathematical formula for the length constant. Conceptually, this formula balances the resistance across the membrane against the resistance along the inside of the axon. The symbol lambda represents the length constant, which is a measure of distance. The variable r subscript m represents the membrane resistance, which is how well the axon membrane prevents electrical current from leaking out. The variable r subscript I represents the internal axial resistance, which is how much the inside of the axon resists the forward flow of current. If we increase membrane resistance by adding a fatty myelin sheath, lambda increases, making conduction faster. Similarly, making the axon wider decreases internal resistance, which also increases lambda and speeds up the signal. Now that we have our length constant formula, let us apply it to compare two different unmyelinated nerve fibers, starting with a narrow one called axon A. We're given that axon A has an internal resistance of 100 ohms and a membrane resistance of 400 ohms. We want to find its length constant to see how quickly its signal decays. We use the length constant formula, substituting 400 for the membrane resistance in the numerator and 100 for the internal resistance in the denominator. Dividing these gives us 4 under the square root. Taking the square root gives us a final length constant of 2. This relatively small number means the electrical signal in this narrow fiber will decay quite quickly as it travels. Having found the length constant for the narrow fiber, let us perform the exact same calculation for a wider fiber, axon B, to see the difference. Because axon B is much wider, its internal resistance drops significantly to 25 ohms, while its membrane resistance remains at 400 ohms. We again use our length constant formula to evaluate its efficiency. We substitute 400 for the membrane resistance and 25 for the new internal resistance. Dividing 400 by 25 yields 16 under the square root. Taking the square root gives us a final length constant of 4. This higher value physically means the signal can travel much further down the axon before it needs to be regenerated. So, we have calculated the length constants for both axons, which brings us to our final logical proof regarding axon efficiency. We set out to prove mathematically why a wider axon is better at conducting signals. By comparing our results, we see that the length constant for axon B is 4, which is exactly twice as large as the length constant of 2 for axon A. The mathematical reasoning here directly translates to biology. The electrical signal in the wider axon can travel twice as far before its voltage drops significantly. Because the signal reaches further before needing regeneration, the overall conduction velocity is much faster. This perfectly illustrates the evolutionary proof of why animals like giant squids developed massive axons for rapid escape reflexes. This mathematical proof of efficiency perfectly sets up what we are looking at in this diagram, which compares two physical modes of conduction. On the top, you see continuous conduction in an unmyelinated axon. Notice the closely spaced plus and minus signs along the entire membrane, representing the local currents that must be regenerated step by step, which we now know is slower. On the bottom, you see saltatory conduction in a myelinated axon. The gray blocks represent the insulating myelin sheath, which increases membrane resistance. The curved arrows show the electrical signal literally jumping from one gap, called a node of Ranvier, to the next. This visualizes exactly how increasing the length constant allows the signal to skip down the axon, resulting in lightning-fast communication. We have covered a lot of ground today, so let us summarize the most important ideas from this topic. First, action potential conduction is a vital physiological process that relies on a continuous chain reaction of depolarization, much like a stadium wave. Second, we learned that the speed of this conduction can be calculated using basic physics and is heavily influenced by the physical properties of the axon. Finally, through the mathematics of the length constant, we proved that increasing axon diameter or adding a myelin sheath allows the signal to travel further and faster. You now have a complete understanding of how our nervous system is beautifully optimized for high-speed communication. Great job following along.